Computer graphics. Computer graphics refers to the creation and manipulation of digital images, videos, and animations using computers and specialized software. Some key points to keep in mind when discussing computer graphics include hardware acceleration. This refers to the use of specialized hardware, such as graphics processing units, GPUs, to increase the performance of graphical operations. Image representation. This refers to the ways in which digital images are stored and represented in computer memory. Common formats include raster images, e.g. JPEG, PNG, and vector images, e.g. SVG, AI. 2D and 3D graphics. Two-dimensional, 2D, graphics refer to images that exist in a two-dimensional plane, while three-dimensional, 3D, graphics refer to images that have depth and can be viewed from multiple angles. Rendering. This refers to the process of generating a final image or animation from a 3D model or scene description. Shading. This refers to the process of adding visual detail to 3D models, such as by simulating the way light interacts with surfaces. Animation. This refers to the creation of moving images, typically by specifying the changes that occur over time to a 3D model or a series of 2D images. Interactivity. This refers to the ability for users to interact with graphical objects and images, for example, by clicking on them, dragging them, or rotating them in 3D space. Virtual and augmented reality. These terms refer to the use of computer graphics to create virtual environments that users can interact with, or to overlay digital information onto the real world. Applications of computer graphics with examples. Computer graphics has a wide range of applications, including multimedia and entertainment. Computer graphics are widely used in the production of movies, television shows, video games, and other forms of multimedia entertainment. For example, the majority of the special effects in modern movies are created using computer graphics. Advertising and marketing. Computer graphics are frequently used to create eye-catching advertisements, product visualizations, and other marketing materials. For example, product packaging design and 3D product visualization can be done using computer graphics. Education and training. Computer graphics can be used to create interactive and engaging educational and training materials, such as animations, simulations, and virtual reality environments. Architecture and interior design. Computer graphics can be used to create 3D models of buildings and interiors, allowing architects and designers to visualize and communicate their ideas to clients. Scientific visualization. Computer graphics are widely used in a variety of scientific fields, such as medicine, engineering, and astrophysics, to visualize complex data, simulate phenomena, and communicate results. Automotive design. Computer graphics are widely used in the automotive industry to design and model cars, trucks, and other vehicles. Art and design. Computer graphics are widely used in the creation of digital art, graphic design, and other forms of visual communication. Web design. Computer graphics are widely used in web design to create website layouts, graphics, and animations. Types of computer graphics. There are two main types of computer graphics: 2D graphics and 3D graphics. 2D graphics, also known as bitmap graphics. 2D graphics are flat, two-dimensional images made up of pixels. These images are used for a variety of purposes, including digital art, web graphics, game graphics, and user interface design. Some common file formats for 2D graphics include JPEG, PNG, and GIF. 3D graphics. 3D graphics are digital representations of three-dimensional objects and environments. These graphics are used in a variety of applications, including video games, architectural visualization, product design, and scientific visualization. 3D graphics can be rendered in real time, which allows for interactive experiences, or offline, which results in high-quality, photorealistic images and animations. Some common file formats for 3D graphics include OBJ, FBX, and Collada. In addition to these two main types of computer graphics, there are several subcategories, such as vector graphics, raster graphics, and motion graphics. Each type of computer graphic has its own unique characteristics, strengths, and weaknesses, and is used in specific applications and industries. Interactive graphics system components. An interactive graphics system typically consists of the following components. Input devices. These devices allow users to interact with the graphics system, such as through mouse clicks, touch gestures, or keyboard input. Some examples of input devices include mice, touchpads, keyboards, and game controllers. Graphics hardware. This includes specialized hardware, such as graphics processing units, GPUs, that is designed to quickly and efficiently process graphics-related tasks, such as rendering 3D images or performing complex mathematical operations. Graphics software. This includes the operating system, drivers, and specialized graphics software, such as game engines or 3D modeling tools, that runs on the computer and communicates with the graphics hardware. Display device. This is the screen that displays the graphics generated by the computer. Display devices can include traditional monitors, laptops, smartphones, and virtual reality headsets. Interaction software. This is the software that mediates between the user's input and the graphics system, determining how the user's actions should influence the graphics that are displayed on the screen. Memory. This includes the computer's main memory, RAM, and secondary storage, e.g. hard drives or solid-state drives, which are used to store the data and instructions required to create and manipulate the graphics. Central Processing Unit, CPU. This is the main processing component of the computer, which is responsible for executing instructions and performing mathematical calculations. The CPU works in conjunction with the GPU to process graphics-related tasks. The components of an interactive graphics system work together to create a seamless and immersive experience for the user. By processing graphics-related tasks quickly and efficiently, the system is able to display high-quality graphics in real time, allowing the user to interact with the graphics in meaningful ways. Cathode ray tube display. A cathode ray tube, CRT, display is a type of display technology that was widely used in older televisions and computer monitors. The CRT works by directing a beam of electrons onto a phosphor-coated screen, which emits light in response to the impact of the electrons. Here is a detailed explanation of the components of a CRT display and how they work. Connector pins. The CRT has a set of pins at the base that connect to the electronics that drive the display. The pins provide electrical connections for the various components of the CRT. Base. The base of the CRT houses the electronics that drive the display, including the electron gun and the deflection circuits. Electron gun. The electron gun is the source of the electron beam that is directed onto the screen. The gun consists of a heated cathode, which emits electrons, and an anode, which accelerates the electrons and directs them towards the screen. Control grid voltage. The control grid voltage is used to control the intensity of the electron beam. By adjusting the voltage of the control grid, the number of electrons that reach the screen can be controlled, which in turn controls the brightness of the displayed image. Focusing system. The focusing system uses a combination of magnetic and electric fields to focus the electron beam into a narrow, well-defined beam. This ensures that the electrons reach the screen with the correct energy and spread, resulting in a clear, sharp image. X deflect and Y deflect. The X deflect and Y deflect circuits are used to control the position of the electron beam on the screen. By adjusting the voltage on the deflector plates, the position of the beam can be changed, allowing the beam to be directed to different parts of the screen. Phosphor screen. The phosphor screen is coated with a layer of phosphors that emit light in response to the impact of the electrons. The phosphors are carefully chosen and arranged to produce the desired color and brightness of the display. Here is a step-by-step process of how a CRT display works. The electron gun heats the cathode, causing it to emit electrons. The anode accelerates the electrons and directs them towards the screen. The focusing system focuses the electron beam into a narrow, well-defined beam. The X deflect and Y deflect circuits adjust the position of the beam on the screen. The control grid voltage adjusts the intensity of the electron beam, controlling the brightness of the displayed image. The electrons hit the phosphor screen, causing the phosphors to emit light. The combination of the various components produces a visible image on the screen. CRT displays have since been replaced by more advanced display technologies, such as LCD and OLED displays, due to their size, weight, and power consumption. However, CRT displays remain an important piece of technology in the history of displays and continue to be used in specialized applications where their unique characteristics are required. Random scan display. A random scan display is a type of display technology that was used in early computer graphics systems. Unlike a raster scan display, which draws an entire image on the screen in a single pass, a random scan display only draws the parts of the image that have changed since the last refresh. Here is a step-by-step explanation of how a RSD works. The computer's graphics software determines which parts of the image have changed since the last refresh. The electronics of the display send a signal to the electron gun to draw only the changed parts of the image on the screen. The electron gun draws the changed parts of the image on the screen by directing a beam of electrons onto the phosphor-coated screen. The phosphors on the screen emit light in response to the impact of the electrons, creating the visible part of the image. The process is repeated for each refresh of the screen, with the electron gun only drawing the parts of the image that have changed. A key advantage of random scan displays is that they require less processing power and memory than raster scan displays, as only the changed parts of the image need to be drawn. This made random scan displays well suited for use in early computer graphics systems, where processing power and memory were limited. However, random scan displays have a number of disadvantages, such as flickering and slower refresh rates, which led to their replacement by raster scan displays in most applications. Today, random scan displays are no longer used in modern computer graphics systems and have been replaced by more advanced display technologies. Input and output devices on computer graphics. Input devices are hardware components that are used to capture information and send it to a computer for processing. Output devices are hardware components that are used to display information that has been processed by a computer. In computer graphics, both input and output devices play a critical role in the creation, manipulation, and display of images. Here are some common input and output devices used in computer graphics. Input devices. Keyboard. The keyboard is an input device used to enter text and control the computer. In computer graphics, the keyboard is used to input commands and control the movement of the cursor on the screen. Mouse. The mouse is an input device used to control the movement of the cursor on the screen and to select objects on the screen. In computer graphics, the mouse is often used to manipulate images and control various functions in graphics software. Graphics tablet. A graphics tablet is a specialized input device that allows for precise input and control of the cursor on the screen. Graphics tablets are often used by digital artists and designers to create images and control various functions in graphics software. Scanner. A scanner is an input device used to digitize physical images and documents. In computer graphics, scanners are used to convert physical images into digital form for use in graphics software. Output devices. Monitor. A monitor is an output device used to display information on a computer. In computer graphics, monitors are used to display images, either in color or black and white. Printer. A printer is an output device used to produce a physical copy of a document or image. In computer graphics, printers are used to produce high-quality images and graphics on paper. Projector. A projector is an output device used to display images and videos on a large screen. In computer graphics, projectors are used to display images and animations in presentations and other large-scale events. These are some of the most common input and output devices used in computer graphics. The choice of input and output devices will depend on the specific needs and requirements of the user and the task being performed. Digital Differential Analyzer (DDA). The Digital Differential Analyzer (DDA) is a scan conversion line algorithm used in computer graphics to determine the intermediate points between two endpoints of a line. The algorithm uses simple arithmetic operations to calculate the positions of the pixels that lie on the line between the two endpoints. Here is a step-by-step explanation of how the DDA algorithm works. Step 1. The two endpoints of the line are defined. Let's call them x1, y1 and x2, y2. Step 2. The difference between the x and y coordinates of the two endpoints is calculated. Let's call these dx and dy, respectively. Step 3. The slope of the line, m, is calculated as the ratio of the difference in y coordinates to the difference in x coordinates, m is equal to dy dx. Step 4. If the slope of the line is greater than 1, the x-coordinate is incremented by 1 for each iteration of the algorithm, and the y-coordinate is updated using the formula y is equal to y plus m. Step 5. If the slope of the line is less than 1, the y-coordinate is incremented by 1 for each iteration of the algorithm, and the x-coordinate is updated using the formula x is equal to x plus 1 slash m. Step 6. If the slope of the line is equal to 1, both the x-coordinate and y-coordinate are incremented by 1 for each iteration of the algorithm. Step 7. The algorithm continues until the final endpoint of the line is reached. Step 8. The pixels at the intermediate positions calculated by the DDA algorithm are plotted on the screen to produce the line. The DDA algorithm is fast and simple, making it a popular choice for basic line drawing in computer graphics. However, it is not as accurate as other line drawing algorithms, such as the Bresenham line algorithm, and can produce visible artifacts on the line. Nevertheless, the DDA algorithm remains a useful tool for understanding the basics of line drawing in computer graphics. Bresenham's line algorithm. Bresenham's line algorithm is a popular scan conversion line algorithm used in computer graphics to determine the intermediate pixels that lie on a straight line between two endpoints. The algorithm uses only integer calculations, making it faster and more efficient than other line drawing algorithms that use floating point arithmetic. Here is a step-by-step explanation of how the Bresenham's line algorithm works. Step 1. The two endpoints of the line are defined. Let's call them x1 y1 and x2 y2. Step 2. The difference between the x and y coordinates of the two endpoints is calculated. Let's call these dx and dy, respectively. Step 3. The decision parameter, p, is initialized to 2 asterisk dy dx for the first point. Step 4. The algorithm iterates over the x-coordinate of the line, starting from x1 and ending at x2. Step 5. For each iteration, the algorithm checks the value of p. If p is less than or equal to 0, the next point on the line is x plus 1, y. If p is greater than 0, the next point on the line is x plus 1, y plus 1. Step 6. The value of p is updated for each iteration using the formula p is equal to p plus 2 asterisk dy, 2 asterisk dx asterisk, y plus 1 y. Step 7. The algorithm continues until the final endpoint of the line is reached. Step 8. The pixels at the intermediate positions calculated by the Bresenham's line algorithm are plotted on the screen to produce the line. The Bresenham's line algorithm is efficient and accurate, making it a popular choice for line drawing in computer graphics. It is used in a variety of applications, including graphics editors, computer-aided design (CAD) systems, and video games. The algorithm's simplicity and efficiency make it a useful tool for understanding the basics of line drawing in computer graphics. 2D translation. 2D translation in computer graphics refers to the process of moving an object from one location to another in a two-dimensional space. Translation is achieved by adding a translation vector to the coordinates of each point in the object. The translation vector specifies the direction and magnitude of the translation. Here is an example to demonstrate 2D translation in computer graphics. Suppose we have a square with the vertices 1, 1, 1, 3, 3, 3, and 3, 1, and we want to translate it by a vector 2, 4. The steps to perform the translation would be as follows. Represent the original square by its vertices in a 2D coordinate system. Define the translation vector 2, 4, which represents the magnitude and direction of the translation. For each vertex in the square, add the translation vector to its coordinates. For example, the vertex 1, 1 becomes 1 plus 2, 1 plus 4 is equal to 3, 5. Plot the translated square using the updated vertices. Repeat the translation as many times as desired to achieve the desired effect. In computer graphics, 2D translation is a fundamental operation that is used in many different applications, including image processing, animation, and user interfaces. The simplicity and versatility of the 2D translation operation make it an important tool for a wide range of computer graphics applications. 2D rotation. 2D rotation in computer graphics refers to the process of rotating an object around a fixed point in a two-dimensional space. Rotation is achieved by transforming each point in the object using a rotation matrix. Here is an example to demonstrate 2D rotation in computer graphics. Suppose we have a square with the vertices 1, 1, 1, 3, 3, 3, and 3, 1, and we want to rotate it by an angle of 90 degrees around the origin 0, 0. The steps to perform the rotation would be as follows. Represent the original square by its vertices in a 2D coordinate system. Define the angle of rotation, in this case 90 degrees. For each vertex in the square, transform its coordinates using the 2D rotation matrix. X is equal to x asterisk cos theta, y asterisk sin theta. Y is equal to x asterisk sin theta plus y asterisk cos theta, where x, y are the original coordinates of the vertex x, y, are the rotated coordinates and theta is the angle of rotation. Plot the rotated square using the updated vertices. Repeat the rotation as many times as desired to achieve the desired effect. In computer graphics, 2D rotation is a fundamental operation that is used in many different applications, including image processing, animation, and user interfaces. The simplicity and versatility of the 2D rotation operation make it an important tool for a wide range of computer graphics applications. 2D scaling. 2D scaling in computer graphics refers to the process of changing the size of an object in a two-dimensional space. Scaling is achieved by transforming each point in the object using a scaling matrix. Here is an example to demonstrate 2D scaling in computer graphics. Suppose we have a square with the vertices 1, 1, 1, 3, 3, 3, and 3, 1, and we want to scale it by a factor of 2 in both the x and y directions. The steps to perform the scaling would be as follows. Represent the original square by its vertices in a 2D coordinate system. Define the scaling factors in the x and y directions, in this case 2. For each vertex in the square, transform its coordinates using the 2D scaling matrix. X is equal to x asterisk sx. Y is equal to y asterisk sy. Where x, y are the original coordinates of the vertex, x, y are the scaled coordinates, and sx and sy are the scaling factors in the x and y directions, respectively. Plot the scaled square using the updated vertices. Repeat the scaling as many times as desired to achieve the desired effect. In computer graphics, 2D scaling is a fundamental operation that is used in many different applications, including image processing, animation, and user interfaces. The simplicity and versatility of the 2D scaling operation make it an important tool for a wide range of computer graphics applications. 2D reflection. 2D reflection in computer graphics refers to the process of flipping an object over a line or an axis in a two-dimensional space. Reflection is achieved by transforming each point in the object using a reflection matrix. Here is an example to demonstrate 2D reflection in computer graphics. Suppose we have a square with the vertices 1, 1, 1, 3, 3, 3, and 3, 1, and we want to reflect it over the x-axis. The steps to perform the reflection would be as follows. Represent the original square by its vertices in a 2D coordinate system. Define the line or axis of reflection, in this case the x-axis. For each vertex in the square, transform its coordinates using the 2D reflection matrix. X is equal to x. Y is equal to y. Where x, y are the original coordinates of the vertex, x, y are the reflected coordinates. Plot the reflected square using the updated vertices. Repeat the reflection as many times as desired to achieve the desired effect. In computer graphics, 2D reflection is a fundamental operation that is used in many different applications, including image processing, animation, and user interfaces. The simplicity and versatility of the 2D reflection operation make it an important tool for a wide range of computer graphics applications. 2D shearing. 2D shearing in computer graphics refers to the process of slanting an object in a two-dimensional space. Shearing is achieved by transforming each point in the object using a shearing matrix. Here is an example to demonstrate 2D shearing in computer graphics. Suppose we have a square with the vertices 1, 1, 1, 3, 3, 3, and 3, 1, and we want to shear it along the x-axis by a factor of 0.5. The steps to perform the shearing would be as follows. Represent the original square by its vertices in a 2D coordinate system. Define the axis and the factor of shearing, in this case the x-axis, and a factor of 0.5. For each vertex in the square, transform its coordinates using the 2D shearing matrix. X is equal to x plus k asterisk y. Y is equal to y, where x, y are the original coordinates of the vertex, x, y are the sheared coordinates, and k is the shearing factor along the x-axis. Plot the sheared square using the updated vertices. Repeat the shearing as many times as desired to achieve the desired effect. In computer graphics, 2D shearing is a useful operation that is used in many different applications, including image processing, animation, and user interfaces. The shearing operation can be used to achieve a wide range of visual effects, such as perspective distortion and isometric projection. 3D translation. 3D translation in computer graphics refers to the process of moving an object in a three-dimensional space. Translation is achieved by transforming each point in the object using a translation matrix. Here is an example to demonstrate 3D translation in computer graphics. Suppose we have a cube with the vertices 1, 1, 1, 1, 1, 3, 1, 3, 1, 1, 3, 3, 3, 1, 1, 3, 1, 3, 3, 3, 1 and 3, 3, 3, and we want to translate it along the x-axis by a distance of 2 units. The steps to perform the translation would be as follows. Represent the original cube by its vertices in a 3D coordinate system. Define the direction and the distance of translation, in this case the x-axis and a distance of 2 units. For each vertex in the cube, transform its coordinates using the 3D translation matrix. X is equal to x plus dx. Y is equal to y. Z is equal to z, where x, y, z are the original coordinates of the vertex, x, y, z are the translated coordinates, and dx is the translation distance along the x-axis. Plot the translated cube using the updated vertices. Repeat the translation as many times as desired to achieve the desired effect. In computer graphics, 3D translation is a fundamental operation that is used in many different applications, including 3D modeling, animation, and virtual reality. The simplicity and versatility of the 3D translation operation make it an important tool for a wide range of computer graphics applications. 3D scaling. 3D scaling in computer graphics refers to the process of changing the size of an object in a three-dimensional space. Scaling is achieved by transforming each point in the object using a scaling matrix. Here is an example to demonstrate 3D scaling in computer graphics. Suppose we have a cube with the vertices 1, 1, 1, 1, 1, 3, 1, 3, 1, 1, 3, 3, 3, 1, 1, 3, 1, 3, 3, 3, 1 and 3, 3, 3, and we want to scale it along the x-axis by a factor of 2. The steps to perform the scaling would be as follows. Represent the original cube by its vertices in a 3D coordinate system. Define the axis and the factor of scaling, in this case the x-axis and a factor of 2. For each vertex in the cube, transform its coordinates using the 3D scaling matrix. X is equal to sx asterisk x. Y is equal to y. Z is equal to z, where x, y, z are the original coordinates of the vertex, x, y, z are the scaled coordinates, and sx is the scaling factor along the x-axis. Plot the scaled cube using the updated vertices. Repeat the scaling as many times as desired to achieve the desired effect. In computer graphics, 3D scaling is a powerful operation that is used in many different applications, including 3D modeling, animation, and virtual reality. The scaling operation can be used to achieve a wide range of visual effects, such as zooming in and out and changing the perspective of an object. 3D rotation. 3D rotation in computer graphics refers to the process of rotating an object in a three-dimensional space. Rotation is achieved by transforming each point in the object using a rotation matrix. Here is an example to demonstrate 3D rotation in computer graphics. Suppose we have a cube with the vertices 1, 1, 1, 1, 1, 3, 1, 3, 1, 1, 3, 3, 3, 1, 1, 3, 1, 3, 3, 3, 1 and 3, 3, 3, and we want to rotate it around the z-axis by 90 degrees. The steps to perform the rotation would be as follows. Represent the original cube by its vertices in a 3D coordinate system. Define the axis and the angle of rotation, in this case the z-axis and 90 degrees. For each vertex in the cube, transform its coordinates using the 3D rotation matrix. X is equal to x asterisk cos theta, y asterisk sin theta. Y is equal to x asterisk sin theta plus y asterisk cos theta. Z is equal to z, where x, y, z are the original coordinates of the vertex, x, y, z are the rotated coordinates, and theta is the angle of rotation in radians. Plot the rotated cube using the updated vertices. Repeat the rotation as many times as desired to achieve the desired effect. In computer graphics, 3D rotation is a fundamental operation that is used in many different applications, including 3D modeling, animation, and virtual reality. The 3D rotation operation allows objects to be viewed from different angles, creating a more dynamic and engaging visual experience. 3D reflection. 3D reflection in computer graphics refers to the process of mirroring an object in a three-dimensional space along a plane of reflection. Reflection is achieved by transforming each point in the object using a reflection matrix. Here is an example to demonstrate 3D reflection in computer graphics. Suppose we have a cube with the vertices 1, 1, 1, 1, 1, 3, 1, 3, 1, 1, 3, 3, 3, 1, 1, 3, 1, 3, 3, 3, 1 and 3, 3, 3, and we want to reflect it along the xz plane. The steps to perform the reflection would be as follows. Represent the original cube by its vertices in a 3D coordinate system. Define the plane of reflection, in this case the xz plane. For each vertex in the cube, transform its coordinates using the 3D reflection matrix. X is equal to x. Y is equal to y. Z is equal to z, where x, y, z are the original coordinates of the vertex, x, y, z are the reflected coordinates. Plot the reflected cube using the updated vertices. Repeat the reflection as many times as desired to achieve the desired effect. In computer graphics, 3D reflection is a useful operation that can be used to create symmetrical objects and to generate reflections in mirrors, water surfaces, and other reflective surfaces. By reflecting an object along different planes, it is possible to create a wide range of visually interesting and complex shapes. 3D shearing. 3D shearing in computer graphics refers to the process of distorting an object along one or more of its axes in a three-dimensional space. Shearing is achieved by transforming each point in the object using a shearing matrix. Here is an example to demonstrate 3D shearing in computer graphics. Suppose we have a cube with the vertices 1, 1, 1, 1, 1, 3, 1, 3, 1, 1, 3, 3, 3, 1, 1, 3, 1, 3, 3, 3, 1 and 3, 3, 3, and we want to shear it along the x-axis by a factor of 0.5 in the y direction. The steps to perform the shearing would be as follows. Represent the original cube by its vertices in a 3D coordinate system. Define the axis and the shearing factor along that axis, in this case the x-axis, and a factor of 0.5 in the y direction. For each vertex in the cube, transform its coordinates using the 3D shearing matrix. X is equal to x. Y is equal to y plus 0.5 asterisk x. Z is equal to z, where x, y, z are the original coordinates of the vertex, x, y, z are the sheared coordinates. Plot the sheared cube using the updated vertices. Repeat the shearing as many times as desired to achieve the desired effect. In computer graphics, 3D shearing is a useful operation that can be used to create objects with slanted or tilted appearances, such as inclined buildings or sloping terrain. It can also be used to create visual effects, such as a skewed perspective or a distorted image. Clipping in computer graphics. Clipping in computer graphics is the process of removing parts of a graphics object that are outside a specified clipping region. The clipping region is defined by a rectangular or a more complex shape window. Some key points about clipping in computer graphics are: clipping algorithms. There are several algorithms used for clipping, such as Cohen-Sutherland, Cyrus-Beck, and Lion-Barsky, among others. Each algorithm has its strengths and weaknesses, and the choice of algorithm depends on the specific requirements of the application. Clipping planes. Clipping algorithms are based on the definition of one or more clipping planes, which define the boundaries of the clipping region. Clipping planes can be defined in 3D graphics, but the most common use is in 2D graphics. Clipping in 2D graphics. In 2D graphics, clipping is used to remove parts of a graphics object that are outside the specified window. Clipping algorithms in 2D graphics typically work by checking if each vertex of the object is inside or outside the clipping region. Clipping in 3D graphics. In 3D graphics, clipping is used to remove parts of a graphics object that are outside the viewing volume, defined by the near and far planes of a virtual camera. Clipping algorithms in 3D graphics typically work by checking if each triangle of the object is partially or completely inside the viewing volume. Optimization. Clipping algorithms can be computationally expensive, especially for complex graphics objects. Optimization techniques, such as bounding boxes, can be used to reduce the number of vertices that need to be checked during clipping. Clipping is a fundamental operation in computer graphics and is used in a wide range of applications, from 2D graphics editors and video games to 3D computer-aided design (CAD) and virtual reality (VR) systems. Line clipping in computer graphics. Line clipping is a fundamental operation in computer graphics that involves removing portions of a line that lie outside a specified clip window or viewport. The goal of line clipping is to only display the portion of a line that is visible within the clip window, while removing the invisible portions. Some key points about line clipping are: clipping window. A line clipping algorithm operates on a specified clip window or viewport, which defines the area where the line will be visible. Line classification. Before clipping, each endpoint of the line is classified as being inside, outside, or on the boundary of the clip window. Algorithms. There are several algorithms for line clipping, including Cohen-Sutherland, Lion-Barsky, and Cyrus-Beck, each with its own strengths and weaknesses. Endpoint modification. If one endpoint of the line is inside the clip window and the other is outside, the outside point may need to be modified so that the line is clipped at the boundary of the clip window. Intersection calculation. The clipped line is found by calculating the intersection of the line with the boundaries of the clip window. Display. The clipped line is then displayed within the clip window. Applications. Line clipping is widely used in computer graphics applications such as computer-aided design, CAD, animation, and 3D modeling. Optimization. Line clipping algorithms can be computationally expensive, especially for large numbers of lines. Optimization techniques, such as bounding boxes or spatial indexing, can be used to reduce the number of lines that need to be clipped. Line clipping is a crucial step in many computer graphics algorithms and is used to ensure that only visible portions of objects are displayed on the screen. It is an important tool for controlling what is displayed in the viewport and for improving the overall efficiency and performance of computer graphics systems. Point clipping in computer graphics. Point clipping is a type of clipping operation in computer graphics where only individual points, rather than entire objects, are clipped against a specified region. The goal of point clipping is to determine whether a given point lies inside or outside of the specified region. Some key points about point clipping are: clipping regions. Point clipping operates on a specified region, which can be a rectangle, a polygon, or any other shape. The region defines the area where points are allowed to be displayed, and any points outside of this region are clipped. Point classification. Point clipping starts by classifying the point into one of four categories: inside, outside, on the boundary, or coincident with the boundary of the clipping region. Test against the clipping region. Depending on the classification of the point, it may need to be tested against the clipping region. This can be done using simple mathematical tests, such as point-to-line distance calculations, or using algorithms like the Cohen-Sutherland algorithm. Display or discard. Points that are inside the clipping region are displayed, while points outside the region are discarded. Points on the boundary or coincident with the boundary may or may not be displayed, depending on the specific requirements of the application. Applications. Point clipping is useful in a variety of computer graphics applications, including interactive graphics, image processing, and computer-aided design (CAD) systems. Optimization. Point clipping algorithms can be computationally expensive, especially for large numbers of points. Optimization techniques, such as bounding boxes or spatial indexing, can be used to reduce the number of points that need to be tested during clipping. Point clipping is a simple but important operation in computer graphics and is often used as a building block for more complex clipping algorithms, such as line and polygon clipping. Cohen-Sutherland line clipping in computer graphics. Cohen-Sutherland line clipping is an algorithm used in computer graphics to clip a line to a specified window or viewport. It is one of the simplest and most widely used line clipping algorithms. Some key points about the Cohen-Sutherland line clipping algorithm are: line classification. The algorithm divides the line into four regions, each represented by a unique code based on the position of the endpoints relative to the clip window. Clipping codes. The four regions are: completely inside the clip window, completely outside the clip window, to the left of the clip window, to the right of the clip window, above the clip window, and below the clip window. Endpoint modification. If an endpoint is outside the clip window, it can be modified so that the line is clipped at the boundary of the clip window. Intersection calculation. The clipped line is found by calculating the intersection of the line with the boundaries of the clip window. Display. The clipped line is then displayed within the clip window. Efficiency. The Cohen-Sutherland algorithm is relatively fast and simple, but it can be computationally expensive if the clip window is large and many lines need to be clipped. Optimization techniques, such as bounding boxes or spatial indexing, can be used to reduce the number of lines that need to be clipped and improve the overall performance of the algorithm. The Cohen-Sutherland line clipping algorithm is widely used in computer graphics applications such as computer-aided design, CAD, animation, and 3D modeling. It provides a simple and efficient way to clip lines to a specified window and is a crucial step in many computer graphics algorithms. Projection in computer graphics. Projection is a technique used in computer graphics to represent 3D objects on a 2D display. There are two main types of projections: perspective projection and parallel projection. Perspective projection. In a perspective projection, objects in the scene are projected onto a 2D plane as if viewed from a specific viewpoint. The objects in the scene appear to be smaller as they get further away from the viewpoint, creating a sense of depth and distance. This type of projection is often used to create realistic images, as it simulates the way that the human eye perceives the world. Parallel projection. In a parallel projection, objects in the scene are projected onto a 2D plane without any perspective. All objects in the scene maintain their relative sizes and positions, regardless of their distance from the viewer. This type of projection is often used in technical drawings or architectural designs, as it provides a clear, non-distorted view of the objects in the scene. Both perspective and parallel projections are important techniques in computer graphics, and the choice of projection depends on the specific requirements of the application. For example, in 3D games and movies, perspective projections are used to create a realistic and immersive viewing experience, while in technical drawings and architectural designs, parallel projections are used to provide accurate and non-distorted views of the objects in the scene. Computer graphic curves. Curves are an important aspect of computer graphics and are used to represent smooth and continuous shapes in 2D and 3D graphics. There are several types of curves used in computer graphics, including Bezier curves. Bezier curves are a type of smooth curve that is defined by control points. These curves are widely used in computer graphics for applications such as 2D vector graphics, animation, and user interfaces. B-spline curves. B-spline curves are a type of curve that is defined by a set of control points and basis functions. They are widely used in computer graphics for applications such as 3D modeling and animation. NURBS curves. NURBS, non-uniform rational B-spline curves, are a type of curve that uses non-uniform knot vectors to define the curve. NURBS curves are widely used in computer graphics for applications such as 3D modeling and animation. Parametric curves. Parametric curves are a type of curve that is defined by a set of mathematical equations. These equations define the x, y, and z coordinates of the curve based on a single parameter. Spline curves. Spline curves are a type of curve that is defined by a set of control points and tangent vectors. They are widely used in computer graphics for applications such as 2D vector graphics, animation, and user interfaces. Each of these types of curves has its own strengths and weaknesses, and the choice of curve depends on the specific requirements of the application. For example, Bezier curves are often used for simple 2D graphics, while B-spline and NURBS curves are used for more complex 3D graphics. Regardless of the type of curve, they play an important role in computer graphics, providing smooth and continuous shapes that can be used to represent objects, animations, and user interfaces. Bezier curve. Bezier curves are a type of smooth curve widely used in computer graphics for various applications. Here are some key points about Bezier curves. Defined by control points, Bezier curves are defined by a set of control points which determine the shape and position of the curve. The number of control points depends on the degree of the curve, with higher degree curves having more control points. Smooth and continuous, Bezier curves are smooth and continuous, making them ideal for representing smooth and natural shapes in 2D graphics. Computationally efficient, Bezier curves can be computed efficiently using algorithms such as the de-Castelgio algorithm, making them well-suited for real-time graphics applications. Easy to edit, Bezier curves are easy to edit, as the shape and position of the curve can be adjusted by moving the control points. This makes Bezier curves a popular choice for applications such as vector graphics, animation, and user interfaces. Vector-based, Bezier curves are vector-based, meaning that the curve is defined mathematically rather than as a series of pixels. This makes Bezier curves scalable and resolution independent, as the curve can be rendered at any resolution without losing its shape or accuracy. Basis functions, Bezier curves are based on basis functions, which determine the shape of the curve. The most common basis function used for Bezier curves is the Bernstein polynomial. Degree, the degree of a Bezier curve is defined as the number of control points minus 1. Higher degree curves have more control points and can represent more complex shapes, while lower degree curves have fewer control points and are more straightforward to compute. In summary, Bezier curves are an important type of curve used in computer graphics for their smooth, continuous shapes, efficiency, ease of editing, and vector-based nature. B-spline. B-spline curves are another type of curve widely used in computer graphics for representing smooth and complex shapes. Here are some key points about B-spline curves. Piecewise polynomial, B-spline curves are piecewise polynomial curves, meaning that the curve is defined as a series of polynomials that are stitched together. Smooth and continuous, B-spline curves are smooth and continuous, similar to Bezier curves, making them ideal for representing smooth and natural shapes in 2D graphics. Control points, B-spline curves are defined by a set of control points, similar to Bezier curves, which determine the shape and position of the curve. However, B-spline curves typically use a larger number of control points compared to Bezier curves. Local control, B-spline curves provide local control, meaning that each control point only affects a small region of the curve, rather than the entire curve. This makes B-spline curves well-suited for applications where it is important to preserve local shape and details, such as in modeling and animation. Basis functions, B-spline curves are defined by a set of basis functions, similar to Bezier curves, which determine the shape of the curve. B-spline basis functions are different from Bezier basis functions, as they are defined over a set of knots, rather than being fixed. Knots are an important part of the definition of a B-spline curve, as they determine the location and shape of the polynomial segments that make up the curve. Flexible, B-spline curves are flexible, as the shape of the curve can be adjusted by changing the location and shape of the knots. This makes B-spline curves well-suited for applications where the shape of the curve needs to be adjusted dynamically, such as in animation and modeling. In summary, B-spline curves are an important type of curve used in computer graphics for their smooth, continuous shapes, local control, flexibility, and ability to represent complex shapes using a large number of control points. Illumination model. Illumination models are mathematical representations of light interactions with objects in a scene. They are used in computer graphics to simulate the appearance of objects and their surrounding environment. Here are some key points about illumination models in computer graphics. Surface properties. Illumination models take into account the surface properties of objects, such as their diffuse and specular reflectance, transparency, and surface roughness, to determine how light interacts with the object. Light sources. Illumination models also take into account the properties of light sources, such as their color, intensity, and position, to determine how light is emitted and how it illuminates the scene. Interactions. Illumination models simulate the interactions between light and objects in the scene, including reflection, refraction, and shadowing, to produce a more realistic image. Shading. Illumination models are used to compute the shading of objects in a scene, which is the variation in color or brightness that occurs due to changes in the angle of light, the surface properties of the object, or the position of the light source. Real-time performance. Illumination models are used to generate images in real time, which means they must be computationally efficient and able to produce results quickly. Global illumination. Illumination models can be classified into two main categories: local illumination models and global illumination models. Local illumination models only consider the direct lighting from light sources, while global illumination models take into account indirect lighting, where light is scattered or reflected by other objects in the scene. Realism. The realism of an illumination model depends on how accurately it simulates the interactions between light and objects in the scene. More advanced illumination models, such as global illumination models, typically produce more realistic images but can also be more computationally intensive. In summary, illumination models are an important component of computer graphics as they simulate the interactions between light and objects in a scene to produce a more realistic image. The choice of illumination model depends on the desired level of realism and computational performance. Ambient light. Ambient light is a basic element of computer graphics illumination models. It represents the light that is present in a scene, even when there are no light sources visible. The ambient light is often used to provide a minimum level of illumination to all objects in a scene, which helps to reduce the appearance of dark shadows and produce a more balanced and visually appealing image. Here are some key points about ambient light in computer graphics. Global illumination. Ambient light is a type of global illumination, which means that it illuminates all objects in a scene, regardless of their position relative to light sources. Color. The color of ambient light can be specified in a computer graphics program, and it typically has a neutral color, such as white or gray. Intensity. The intensity of ambient light can also be specified, and it is usually a low value, such as 10% or 20% of the maximum light intensity. This low intensity helps to avoid overexposure of the image and to produce more realistic shadows. Directionality. Ambient light is considered to be omnidirectional, which means that it illuminates objects from all directions. This helps to produce a more evenly lit image, even when the light sources are not directly visible. Interaction with other lights. Ambient light can be combined with other light sources in a scene to produce a more realistic image. For example, ambient light can be used to provide a base level of illumination, while other lights, such as point lights or spot lights, can be used to provide more focused and directional lighting. In summary, ambient light is an important component of computer graphics illumination models, as it provides a base level of illumination to all objects in a scene. It can be used to reduce the appearance of dark shadows and produce a more balanced and visually appealing image. The color intensity. and directionality of ambient light can be specified in a computer graphics program to produce the desired visual effect. Diffuse reflection with example. Diffuse reflection is a fundamental concept in computer graphics that refers to the scattering of light in all directions, causing surfaces to appear evenly lit. Here are some key points to consider when working with diffuse reflection in computer graphics. Diffuse reflection is proportional to the surface normal and the light direction. The intensity of diffuse reflection depends on the angle between the surface normal and the direction of incoming light. The more perpendicular the surface normal is to the light direction, the more intense the diffuse reflection will be. Diffuse reflection models the roughness of surfaces. Diffuse reflection models how rough or smooth a surface is. A smooth surface will scatter light evenly in all directions, while a rough surface will scatter light in many directions, creating a more diffuse reflection. Diffuse reflection is affected by the color of the surface. The color of the surface affects how it reflects light. A red surface, for example, will reflect more red light than other colors, while a white surface will reflect light of all colors. Diffuse reflection is modeled using the Phong reflection model. The Phong reflection model is a widely used model in computer graphics for simulating diffuse reflection. It takes into account the diffuse reflection term, the specular reflection term, and the ambient reflection term to create a more realistic representation of surfaces. Example: consider a red sphere lit by a white light source. The diffuse reflection of the sphere will depend on the angle between the surface normal and the light direction. The sphere will appear brighter where the surface normal is perpendicular to the light direction and darker where the angle is smaller. The color of the sphere will also affect the diffuse reflection, with more red light being reflected from the surface than other colors. This is just a brief overview of diffuse reflection in computer graphics. There is much more to learn about this concept, including how it is affected by other factors such as surface roughness and texture, but this should give you a good starting point. Specular reflection with example. Specular reflection is a concept in computer graphics that refers to the reflection of light from a surface in a single, concentrated direction, giving the surface a shiny appearance. Here are some key points to consider when working with specular reflection in computer graphics. Specular reflection is proportional to the surface normal, the light direction, and the view direction. The intensity of specular reflection depends on the angle between the surface normal, the direction of incoming light, and the direction that the camera is facing. The more perpendicular the surface normal is to the light direction, and the more the view direction aligns with the reflection direction, the more intense the specular reflection will be. Specular reflection models the smoothness of surfaces. Specular reflection models how smooth or rough a surface is. A smooth surface will reflect light in a single direction, while a rough surface will scatter light in many directions, reducing the intensity of the specular reflection. Specular reflection is affected by the color of the surface. The color of the surface affects how it reflects light. A white surface, for example, will reflect more light of all colors than a dark surface. Specular reflection is modeled using the Phong reflection model. The Phong reflection model is a widely used model in computer graphics for simulating diffuse and specular reflection. It takes into account the diffuse reflection term, the specular reflection term, and the ambient reflection term to create a more realistic representation of surfaces. Example: consider a shiny metal ball lit by a white light source. The specular reflection of the ball will depend on the angle between the surface normal, the direction of incoming light, and the direction that the camera is facing. The ball will appear brighter where the surface normal is perpendicular to the light direction and the view direction is aligned with the reflection direction, and darker where the angle is smaller. The color of the ball will also affect the specular reflection, with more light being reflected from a white surface than a dark surface. Visible surface detection with example. Visible surface detection, also known as hidden surface removal, is an important concept in computer graphics that determines which surfaces of 3D objects are visible and which are hidden from the viewpoint of the observer. Here are some key points to consider when working with visible surface detection in computer graphics. Hidden surface removal is important for creating realistic images. In order to create a realistic image of a 3D scene, it's necessary to correctly identify which surfaces are hidden from view and remove them from the image. This helps to avoid visual artifacts, such as objects appearing to be floating in front of other objects, or objects appearing to penetrate each other. There are several algorithms for visible surface detection. There are many algorithms for performing visible surface detection, including backface culling, depth sorting, and Z buffering. Each algorithm has its own strengths and weaknesses, and the choice of algorithm will depend on the specific requirements of the application. Visible surface detection is often performed in hardware. Visible surface detection can be a computationally expensive process, and so it is often performed in hardware to speed up the process. Modern graphics processing units, GPUs, have dedicated hardware for performing visible surface detection. Example: consider a scene with a cube and a sphere, both lit by a light source. The task of visible surface detection is to determine which parts of the cube and sphere are visible from the viewpoint of the observer and to remove the hidden parts from the image. For example, the back faces of the cube are hidden from view, and so these would be removed from the image. Similarly, the inside of the sphere is hidden from view and would also be removed from the image. The resulting image would show only the visible parts of the cube and sphere, creating a more realistic representation of the scene. Back face detection with example. Back face detection is a technique in computer graphics for identifying which surfaces of 3D objects are facing away from the viewpoint of the observer and are therefore not visible. Here are some key points to consider when working with backface detection in computer graphics. Backface detection is a simple and fast algorithm for hidden surface removal. Backface detection is a simple algorithm that can be used to quickly identify hidden surfaces in a 3D scene. The algorithm works by calculating the dot product of the surface normal and the direction from the surface to the viewpoint, and using this to determine which surfaces are facing towards or away from the viewpoint. Backface detection is only appropriate for convex objects. Backface detection is only effective for convex objects, where all surfaces are facing either towards or away from the viewpoint. For concave objects, backface detection may fail to identify all hidden surfaces, as some surfaces may be facing partially away from the viewpoint. Backface detection is often used in conjunction with other techniques. While backface detection can be a fast and effective method for hidden surface removal, it is often used in conjunction with other techniques such as depth sorting or Z buffering to create more accurate and complete images. Example: consider a cube with 6 faces. If the cube is viewed from the front, all 6 faces will be visible. However, if the cube is viewed from the back, only the front face will be visible and the other 5 faces will be hidden. Backface detection can be used to identify which faces of the cube are hidden and to remove them from the image. The algorithm would calculate the dot product of the surface normal and the direction from the surface to the viewpoint, and use this to determine which faces are facing away from the viewpoint and are therefore hidden. Z-buffer method with example. The Z-buffer method, also known as the depth buffer method, is a widely used technique for performing visible surface detection in computer graphics. Here are some key points to consider when working with the Z-buffer method in computer graphics. The Z-buffer method maintains a depth map of the scene. The Z-buffer method maintains a depth map of the scene, with each pixel in the map representing the distance from the viewpoint to the closest object at that position in the scene. This depth map is used to determine which surfaces are visible and which are hidden from the viewpoint. The Z-buffer method uses a two-pass algorithm. The Z-buffer method typically uses a two-pass algorithm, with the first pass computing the depth values for each pixel in the scene, and the second pass rendering the image using the depth information to determine which surfaces are visible and which are hidden. The Z-buffer method is efficient and effective. The Z-buffer method is efficient and effective and is widely used in both hardware and software rendering systems. It can handle complex scenes with a large number of objects and provides accurate and stable results. Example: consider a scene with two overlapping objects, a cube and a sphere. If the cube is closer to the viewpoint than the sphere, the Z-buffer method would render the image so that the cube is visible in front of the sphere. The algorithm would work as follows. During the first pass, the depth values for each pixel in the scene would be computed and stored in the Z-buffer. During the second pass, the image would be rendered by comparing the depth values for each pixel with the values stored in the Z-buffer. If the depth value for a pixel is less than the value stored in the Z-buffer, the pixel is considered to be visible and its color is drawn. If the depth value for a pixel is greater than the value stored in the Z-buffer, the pixel is considered to be hidden and is not drawn. In this example, the Z-buffer method would correctly identify that the cube is in front of the sphere and would render the image so that the cube is visible in front of the sphere. Multimedia with example. Multimedia in computer graphics refers to the use of multiple forms of media, such as images, video, audio, and text, in the creation of computer graphics. Here are some key points to consider when working with multimedia in computer graphics. Multimedia enhances the visual experience. Multimedia can greatly enhance the visual experience of computer graphics by allowing the use of multiple forms of media to create more engaging and dynamic images and animations. Multimedia enables the creation of interactive content. Multimedia also enables the creation of interactive content, such as video games, simulations, and educational software, where the user can interact with the images and media on the screen. Multimedia requires large amounts of data and processing power. Creating multimedia graphics requires large amounts of data and processing power, as the computer must store and manipulate many different forms of media at once. Multimedia can be used for a variety of purposes. Multimedia graphics can be used for a variety of purposes, including entertainment, education, advertising, and more. Example. A simple example of multimedia in computer graphics is a video game where the player controls a character that interacts with the world on the screen. The game might use images, video, audio, and text to create the world and characters, and the player's actions and interactions with the world would be displayed in real time using computer graphics. Animation with example. Animation in computer graphics refers to the creation of moving images and graphics through the use of software and computer algorithms. Here are some key points to consider when working with animation in computer graphics. Animation involves creating the illusion of motion. Animation in computer graphics involves creating the illusion of motion by rapidly displaying a sequence of still images, each slightly different from the previous one. Animation requires a smooth and seamless transition between images. To create a smooth and believable animation, it's important to ensure that there is a seamless transition between each frame in the animation, with no abrupt changes or stuttering. Animation can be used for a variety of purposes. Animation in computer graphics can be used for a variety of purposes, including entertainment, education, advertising, and more. Animation requires a large amount of data and processing power. Creating animation in computer graphics requires a large amount of data and processing power, as the computer must store and manipulate large amounts of image and animation data in real time. Example: a simple example of animation in computer graphics is a bouncing ball animation. The animation would be created by creating a sequence of images that show the ball moving up and down, with each frame in the animation showing the ball slightly higher or lower than the previous frame. To create a believable animation, it's important to ensure that the transition between each frame is smooth and seamless. Video formats with example. Video formats are a type of multimedia format that are used to store and display moving images and audio. There are many different video formats available, each with its own unique features and trade-offs. Here are some key points to consider when working with video formats in computer graphics. Different video formats have different compression methods. Video formats can use different compression methods to reduce the size of the video file while still maintaining the quality of the image. Some video formats are better suited for specific applications. Different video formats are better suited for different applications, depending on the requirements of the project, such as the desired quality, file size, and compatibility with specific devices and software. Some video formats have limited compatibility. Some video formats are only compatible with specific devices, software, and operating systems, so it's important to choose a format that is compatible with the intended audience and distribution platform. Some video formats have limitations on the amount of data that can be stored. Some video formats have limitations on the amount of data that can be stored, such as the maximum resolution, number of colors, and frame rate, which can impact the overall quality of the video. Example: one common video format is MP4, MPEG, 4 Part 14, which is a widely used format that is well suited for many different applications, including web video, mobile devices, and more. MP4 uses a combination of video and audio compression to reduce the size of the video file while still maintaining the quality of the image. Additionally, MP4 is compatible with a wide range of devices, software, and operating systems, making it a popular choice for many different types of video content. JPG compression with example. JPG, Joint Photographic Experts Group, is a commonly used image compression format in computer graphics. The JPG compression algorithm works by dividing an image into small 8x8 pixel blocks and then transforming each block using a mathematical transformation called the discrete cosine transform, DCT. The DCT coefficients are then quantized and encoded using a lossless compression algorithm, such as Huffman coding, to further reduce the size of the image data. Here is an example of how the JPG compression algorithm works in computer graphics. Divide the image into 8x8 blocks. The image is divided into small 8x8 pixel blocks. This allows the compression algorithm to work with small, manageable chunks of data. Apply the DCT. The DCT is applied to each 8x8 block. The DCT transforms the image data from the spatial domain, where each pixel represents a specific location in the image, to the frequency domain, where each coefficient represents a specific frequency component of the image. Quantize the DCT coefficients. The DCT coefficients are then quantized using a quantization matrix. Quantization reduces the number of bits required to represent each coefficient, which results in a reduction in the size of the image data. Encode the quantized coefficients. The quantized coefficients are then encoded using a lossless compression algorithm, such as Huffman coding, to further reduce the size of the image data. The result of the JPG compression algorithm is a compressed image that uses less data to represent the same image content, while still maintaining a reasonable level of quality. The amount of compression achieved by the JPG compression algorithm depends on the quality setting used during the compression process, with higher quality settings resulting in less compression and lower quality settings resulting in more compression. In computer graphics, JPG compression is commonly used for digital photographs and other types of continuous tone images, as it provides a good balance between image quality and file size. However, it is not as effective for images with sharp transitions and large areas of flat color, as the quantization process can result in noticeable degradation of image quality in these areas. Like, share, subscribe for more videos. Thank you for watching.